Hello everyone, Namaste to you all. This is the first episode of the podcast Reason in Science. Today I have a very special guest with me. He is an assistant professor of theoretical physics from York University in Canada. Actually, I got to meet him 5 years back, and it was a very great experience for me as a young student to get to meet him and learn from his experience and expertise. And this is officially the starting of the podcast Reason in Science. I have been trying to do this since a very long time, but due to a lot of difficulties, I couldn't initiate this project. So here we are, and finally, I believe we are all set to go. I will be trying my best to come up with different guests and talk about different intellectual, scientific things that are happening in different fields of science, and try to do the discussion at a level that people can understand. So I am really looking forward to your opinions and your views. So thank you very much and welcome to the podcast. Welcome to the podcast, Dr.
Thank you.
So how was the pandemic experience for you overall?
So personally, for me, it's not that hard because I'm used to, as a theoretical physicist, many of us are used to stay at home and just stay in offices and, not really going out, just work on projects and thought experiments and all of those things. So personally, for me, I'm like an indoor person. It wasn't that hard, but I would assume that it's hard for other people that are more outgoing.
Okay. And what about your university classes? You are teaching right now, right?
Yes. So, right now it's summer, but we will start on end of August, actually September, beginning of September. So the classes are from the middle of the March, it started to be online. So I teach via Zoom and also use some technological, like online whiteboards and slides, all of those things.
Okay. So before formally starting the podcast, let me give you a brief overview of this podcast. So from my observation, I have seen a very big gap between the intellectuals and the common people, the layman people. So we know from experience that many people, they want to do science. They are interested in different topics of science, but due to the lack of expertise, and on the other side, due to the lack of willingness or eagerness of the scientific experts to come and explain their findings to the people, to the public, I have seen a very huge gap. And the motivation behind a program like this is to bridge that gap. And I hope we will be having a lot of discussions today in consideration to that so that general people, laymen, can understand different things. Okay, so let me ask you some personal question. Like, you were born and raised in Iran, right?
Yes.
So a boy born and raised in Iran to a theoretical physicist working in Canada, how do you join these two dots in space time?
So when I was a young kid, probably 7-8 years old, or a bit around that, my mom actually liked a lot like astronomy and being an astronaut. So of course the opportunities are less in Iran to be all those, especially at those times. So anyway, as parents see their hope in their kids, she actually bought me astronomy books for kids, small ones. I remember one of them, actually the name was Black Holes in Persian.
Okay.
So yeah. So
was it some local author or some international author?
I think it was international author, but it was translated into Persian.
Mm-hmm.
So I had several of these. I also had different other books about dinosaurs or other things, but I think that astronomy was the majority of the books. So I would think that was one of the reasons I got interested in astronomy, and then later in physics. So yeah. Well, I was in high school, I made a telescope. And
a telescope.
By myself. So
okay, what was the range and what did you make?
So it was a Newtonian. So it was a Newtonian telescope. The diameter of the mirror was 15 centimeters. And it was the length of the tube was 150 centimeters, a large telescope. Okay. But anyway, so I really enjoyed. I saw the moons of the Galilean moons of Jupiter. The Saturn's ring, all of those with that telescope. I really enjoyed. then so this led to me studying physics, and then I went to do my PhD with one of the leaders of the what we call loop quantum gravity.
So you did your PhD in Iran itself?
In Uruguay. So I did my bachelor's and master's in Iran, and then went to Uruguay under the supervision of my advisor, do my PhD, and then a couple of postdocs in Mexico, and then a position in Mexico, an assistant professor. After 1 year, then I moved to Canada. Now I'm assistant professor here.
Oh, okay, interesting. So from the news, we have heard a lot of like nuclear programs in Iran and things like that. How is the status of science and technology in Iran overall?
Well, there are good universities in Iran. I don't know about that part, the nuclear, but there are good universities in Iran, especially older times. Maybe they were better.
For fundamental sciences or for applied?
For fundamentals, as far as I know. I mean, I'm more in fundamental science. So there's Sharif University.
Yeah, that's a pretty famous one. Yeah.
So yeah, that was. So many of the students that go out of Iran are graduating from that university. And there is Shiraz University. There is Tehran University. So there are good professors. They're doing good job and good students.
Okay. So generally in physics, like we have theoretical physics that is more related to mathematics, and applied physics is more about experimentation and observation, and they go kind of hand in hand. Sometimes the theory leads, and sometimes the applied physics or the experimental physics leads. As for example, Higgs boson, it was predicted in 1964, and finally it was experimentally verified in 2012, and so the theory led here. And for another example, the Hubble expansion of the universe, the experiment led, and then finally it was reconciled into the theoretical framework in 1960s, right? Am I right about the accuracy?
Yes.
So,
about the years, I'm not sure myself, but yeah.
How do you view the relation between theoretical physics and applied physics and experimental physics, like your ideas?
So physics, like other natural sciences or sciences in general, is based on both theoretical. I mean, the logical. It has a logical structure that is theoretical, and also not every logical structure that is sound, that is logical, makes sense, corresponds to nature. So you can have several logical structures, several theories that we call them, but you have to do experiments based on them. So these theories should give you some hints if you want. So for example, a theory says that, okay, I predict that the diameter of the moon should be this kilometer, right? And then you have to go out and do an experiment, precise experiment of the diameter of the moon. And if that corresponds to the theoretical result, it means that your theory partially is approved, not completely. So you have to do lots of these experiments to approve your theoretical results. So it means that although your theory is logically consistent, it also has to correspond to experiments. So as you mentioned, they go hand in hand, and none of them works with the other one. You can have some new particle discovered. If you don't have a good theory for that, you don't know where does it come from, what it is, the particle or something else. On the other hand, if you predict some particle, and if it's never discovered in the nature, it means that your theory is not correct.
So this is my query actually. We say that human beings are just naturally born scientists, and the only way we can pursue theoretical physics is by exploring the limits of human thinking, right? But generally what happens is the human intuition, generally from what we know from our experience from sciences, our intuition does not work, because our intuition corresponds to the three-dimensional Newtonian world, and many theoretical physics stuff that we do, they correspond to a completely different world that we are unaware of, right? But as human beings, we need to adjust here in the three-dimensional Newtonian world and still keep on pursuing the theory of the unknown. So how do you see this anomaly, and what's your...
Yeah, so that's a good question. So the idea here is that's actually what the idea that we do in practically in science when we publish papers and do research. So you have this intuition, as you mentioned, is based on what we call classical Newtonian physics.
Yes.
So just to clear that out, we have classical physics and quantum physics. So whenever you have quantum theory in something, you have quantum physics. Our classical physics itself kind of has three levels. It's Newtonian physics, which is for studying any phenomenon in which there's no very fast velocity, I mean fast corresponding compared to the velocity of light or speed of light, and also if there are no strong gravitational fields or a strong too much acceleration. So this is Newtonian physics. Now, if you want to go to the realm where one of these is relaxed, so you have speeds near the speed of light, but still there's no gravitational field. That's a special relativity. So it's classical, but it's special. It's not quantum, but it has a special relativity, one level better. And then if you have gravitational field and a higher speed, it's called general relativity. It's still classical. And then if you add to any of them, you will have quantum version of any of them. You have quantum special relativity, which is basically quantum field theory. Maybe we talk about it. And then you have quantum general relativity or quantum gravity, all of those. Now, so physicists, what we do that we know that the intuitions not always work, but it works very well for Newtonian physics, right? So when we propose a theory, there is a machinery always to find the classical limit of that theory. So if you have something that doesn't work for intuition, we know that inside of the black holes, things are weird. We don't understand them. But we kind of try to reduce that to see that, okay, if I as a person that my intuition only works for classical Newtonian physics, enter a black hole, what do I see? So I don't really see all those particles and everything. Of course, we don't see the particles, but what
you will feel the
classical
effect.
Sorry,
you will feel the effect of a black hole.
Yeah. So what you feel is the classical results are like kind of classical limit. What we say, it's like an approximation. So your theories should always reduce to those classical limits where it makes sense.
So that's how you know your theory is correct, right?
That's one of the ways. Yes.
So I think that's where the scientific method comes to rescue, because you have a definite formalism, and so that's where experiments need to be done, so as to know exactly if a theory is correct or not. But like generally in quantum field theories, in your field actually, and I have learned that the theories are not testable to a certain degree of accuracy that is needed in order to ascertain that the theory is correct. So in those cases, how are we going to be sure that what we are doing is actually correct?
So first of all, to some degree, all the theories should be able to, you should always be able to test theories to some degree, I mean, to some level. It means that if you have Newtonian physics, you have to be able to test it. You don't need to test it for higher velocities or strong gravitational fields, but you have to be able to do it for small velocities and no gravitational field. And we know by now that almost all of our theories, I would say, are what we call in physics effective theories. Effective theory means a theory that is only valid for a range of certain energies or a range of parameters, right? So classical Newtonian physics is perfectly good and is correct when you don't have higher speeds. But that's an effective theory just for lower speeds, and then you go higher and so all the theories that I know that scientists accept them are actually tested within their own range of parameters. Quantum field theory, for example, especially is one of those that has tested for very precise parameters. And of course, if you want to go to very higher and much higher energies than we call the usual quantum field theory energies, it may not work. We don't know. But it doesn't mean that the theory is wrong. It means that the theory is only valid and completely correct for those range of energies that we work with.
So what about those theories, those different theories which are correct simultaneously in a given range? Is that also the case? Like there can be many different theories which are mutually true in a given range.
I don't know any personally. Maybe it's my lack of knowledge. I don't know any two.
Like for example, when it comes to the idea of unification, like string theory, M theories, right? So there are different versions of it, but we do not. How do we select the best out of them? Like that's
so. First of all, that's the experiment. As far as I know, none of the quantum gravity theories. You have a string theory or M theory. You have loop quantum gravity, which I work on. and you have several versions of this. None of them experimentally at the moment are basically they're shaky. We don't have that many experiments that confirm them, or if you want, well, there are theories that kind of point to the direction that, well, maybe that theory is not correct. So, for example, a string theory is somehow predicts, well, not predicts, but it needs the particles called, or a phenomenon called supersymmetry.
Supersymmetry, exactly, yes.
So at the moment, so there were years and years that people in the string theory were saying, okay, next year this will be discovered, next year.
LHC, you're talking about LHC, right?
LHC, yes. It has not yet been discovered. At the moment, it doesn't rule it out completely, because, I mean, there are other possibilities that this can always be found at higher energies. But this doesn't help the theory in that sense. Like, so yeah, that's the thing, that if you're talking about theories, you have to remember that theories are things that are at the moment, at the same time that their logical structure is sound, they have to be supported by experiments. So if you have two logical structures that are perfectly sound, and as you mentioned, they're competing, experiment is the thing that distinguishes between them. So at the moment, for example, between different versions of a string theory, there's no experiment that distinguishes them, or even distinguishes between M theory and loop quantum gravity. So all of them are just hypotheses, if you want, not
elegant
theories.
Hypotheses.
Just at the beginning of the podcast, maybe I mentioned that you have to, for scientific theories, you have to have two things. The logical structure should be good, and it should be supported by experiment. Many of these theories have the first part. So the logical structure is very good, but the second part, almost all of them lack that at the moment, for technological reasons mostly. And so that's why we don't know which one is correct.
Okay. I think it was back in 2013 or 14, there was a very famous article published in Nature, and it discussed precisely this problem. It was about a school of thought, especially the historians of science, who were asking the scientific community to revise the scientific method itself. Because in scientific method, it is necessary that for a theory to be true, it has to pass the experiment, right? But since many elegant quantum field theories cannot be tested even in the nearby future, so it is better if we just revise it or make some excuse for quantum field theories which are elegant enough. So a theory that is elegant enough is right, and it is not necessary that it needs to pass the experimental test, something like that. I mean, those quantum field theories which try to describe the state of the universe before the 10 to the power minus 43 seconds.
Yeah, the quantum gravity. Those are mostly, we call them quantum gravity, because there also gravity is very strong. So we can talk about that too later. But and then about what you mentioned is that that's a school of thought that it's an old school of thought that they say that beauty is more important than
exactly
truth, maybe. If that's the case, I don't. I mean, that's a good direction.
But historically, it has a very proven track record. If you look at physicists like Dirac and like Feynman.
Yeah, most of the cases, I would say that it's not always true. I mean, the universe could be more. Maybe there are theories that are more beautiful, and they're not like this E8 theory. And not necessarily they're true. I mean, we don't go like that for truth. So beauty and truth, maybe some correlations, but well, we are not. I personally am not. I don't use it only as the unique indicator that the theory is correct.
So your idea is something like, maybe our idea of beauty is best is limited itself. So maybe there is something bigger which we do not know.
That could be. I mean, the beauty I'm talking about is the mathematical beauty, which is unfortunately only people can access that. The people who can access that are the people who are good in mathematics, theoretical physicists. So there are, I mean, I can talk about the symmetry in physics, which is very, very beautiful, and that's basically if you ask me that. Let's strip everything away from human knowledge about physics and just give you one concept, and from that you can build up the rest of the physics. I would say that's symmetry. But when I say symmetry, many people think about different things. Somebody thinks about the symmetry of a circle, right? Which is a symmetry.
Yes.
But when we talk about symmetry in physics, it's much, much more deeper. You need a lot of years to study mathematics and everything. And so that beauty is a little bit less subjective, if you want. So more like mathematical, more logical. But returning back to what you mentioned about the historians of science, is that to some extent, in one way, they're correct, and people are doing that. For example, they're trying to find phenomenological signatures of quantum gravity to be, at the end, to be able to test it with something, because at the end we need that, right? And we cannot wait for 200 years to get a technological device like LHC that can measure a lot of higher energies than what we have. So in that sense, yeah, many of physicists are actually leaning towards that. Let's find something, at least to, a few experiments to lower the level of accuracy a little bit, just to see where does things go.
Okay, so what research are you doing these days? What research are you busy with?
So I'm working on, in general, it's called quantum gravity, as you mentioned. That's the realm where, you remember I said classical physics is low velocity, then high velocity, then strong gravity. So a strong gravity, or general relativity, which explains the curvature of the space-time, basically, which is a very awkward thing. When you combine that with quantum theory, it's called quantum gravity. So usually in universe, most of the universe is such that either the quantum effects are very important or the gravitational effects. However, there are places that, so we have theories, when the quantum effect is very important, we can use quantum theory. When the gravitational effect, we can use quantum theory apart from relativity or anything, general relativity. If gravity is strong, we can neglect quantum theory and just use general relativity. But when both of them are strong, we cannot neglect any of them, and we have to use a theory that is a combination of both in some ways. It's called quantum gravity. That's, for example, interior of the black holes, near the singularity, and also very early universe, like the first few nanoseconds or something, or even earlier. So those places are the places that you have to combine quantum theory and relativity, general relativity, to find something. And we don't have that theory yet. So we don't have any theory of quantum gravity. We're just guessing things together, but nobody has it yet. And that's my field of work. And in that field of work, mostly I'm concentrated on the black holes. So what happens inside the quantum black hole, if you want.
And there could be other different quantum field theories which exactly try to unify the quantum theory and the general theory of relativity. Or like, what about M theories and brane theories? There are so many quantum field theories, I guess.
So the quantum gravity, I would say that quantum gravity, you can divide it into two categories. And remember, when I say gravity, gravity is a space-time, and a space-time is gravity. So you can either think about a force of gravity, or you can think of a space-time. They're the same thing. In the relativistic point of view, if I may, you can think that there is no such thing as gravity. Just
curvature of space-time is gravity.
So exactly. So if you consider curvature of space-time, don't think about gravity, because you already have that. So they're not two things, they're two different things. They're the same thing. Okay. Now, so when I say quantum gravity, it also means quantum space-time. So it's not usual smooth space-time. It's a weird thing that is underlying this space-time. It's kind of, you can think of that as if you look at water. So in water, our intuition, what we see is a smooth thing, is a continuous smooth thing that is flowing.
Yes.
But in reality, if you look at it with a high-powered lens, you will see that there are particles. Actually, it's not continuous at all. It's discrete, and these particles are bouncing on each other and going around. So, and that's the real nature of to that level of the magnification is the real nature of fluid or water. So that's the same for a space-time. When I say quantum structure of space-time, I mean that space-time really may not be that smooth thing that we are observing every day and float in it. So it may be something that's discrete, and but you have to look at it with a very strong lens. Okay, so yeah, so there are two types of quantum gravity theories. One, we call them bottom-up. The other one is top-down. So top-down is that. Yeah, so top-down is when you have a classical theory, like classical space-time, classical general relativity, right? And then I take it and apply quantum theory to it.
try to quantize it.
Quantize it. So that's exactly like what we do to, for example, fluids. You take fluids and then we say that, okay, what happens if I quantize it? It means that in a very naive sense, it means that you just divide it into a small small particles and see what happens. The other version is that they say that, okay, no, maybe you cannot do that. You have to do the other way. Take a small quantum of objects. We don't know what they are. Maybe they are particles, whatever. There are some things, and then look at them from very far away to an extremely large number of those small objects that, again, we don't know if they're particles, if they're strings, if they're whatever they are. So this way is like, again, looking at water or a gas, particles of the gas, but from our viewpoints, not from the viewpoint of a lens.
Okay.
And then we see that as a continuous thing. So there's a difference between these two, is that mostly bottom-up theories or approaches assume that you cannot do a top-down approach, actually. So an example is thermodynamics. Okay, so physicists know that when you have thermodynamics that explains the properties of a continuous gas, for example, the basic properties of volume and the temperature and pressure, right? You can never quantize that and get the statistical mechanics. So statistical mechanics is the science that explains the movement of these small particles, right, of the gas. Assuming that gas is not continuous, it's a bunch of particles. You can never quantize thermodynamics to get the statistical mechanics. However, you can take the statistical mechanics and look at it like a gas, look at it from far away, what we call coarse graining, and then you can get thermodynamics.
Yes.
And the properties of these systems are absolutely different. So the properties of a gas, if you look at it, which is a less accurate version of nature, it is, as I mentioned, volume, pressure, and temperature. But the properties of particles in the gas, the statistical mechanics, is like velocity or momentum, velocity and position, all these things. Velocity and position does not make sense for a gas. On the other hand, volume and temperature does not make sense for a particle. So there are two different levels of nature, if you want. But you cannot quantize one to get to the other one. You have to coarse grain one, the lower one to get to the higher one. So these are the two categories of physics, and to quantum gravity. And to answer your question, the top-down approaches that to quantize a classical theory, loop quantum gravity is one of them, a string theory is one of them, and there's a difference between these two. The string theory comes from the quantum field theory community. So they're more concerned about particle nature of the universe and all of these things. But loop quantum gravity comes from the gravity community. So we are more concerned about the space-time. So you can look at the universe. Universe has basically two components: all the particles and the space-time. Particles are moving on the space-time. So field theory people or string theory people are more concerned about the particle part. We, as gravity physicists or loop quantum gravity community, are more concerned about the space-time part, gravity part.
So interesting. So when you talked about thermodynamics, I just thought of entropy and the arrow of time. So what do you have to say about the arrow of time? Like, does time really exist as a physical entity, or is it just a psychological thing out of human mind?
That's a long standing and hard question. Nobody really knows what. I mean, in my opinion, time is one of those subjects that whenever you think about it, it gives birth to new theories. Sometimes revolutions, like the general relativity was one of them. Think hard about time and changing the notion of time. That before Einstein, time was something that was always there, never changing. But then he came on and mentioned that actually simultaneity of two events in the universe is actually relative. It's relative. Not if two events happen at the same time for me, it may not happen at the same time for you, and all of those things. So time is still a mystery as a space is, but I would say that time is even more mystical or no, mysterious. If you want. Yes. So.
Oh, okay. Sorry to interrupt. Yes, you may.
No. Just to mention that the arrow of time, there are lots of things that can be said about that. But as you mentioned, it's very related to the the second law of thermodynamics, the entropy.
The reason I ask this question is because I have read a lot of articles where many authors, they thought of time as being very critical when it comes to the idea of unification of quantum theory and the general theory of relativity. So as a researcher who is exactly working in quantum gravity theory, like what's your impression about time? Do you think that any kind of unification theory that is of our future, a scientifically valid one, do you think that will involve time in some way, or what's your opinion about it?
They have to at least explain where time comes from. So either time is a fundamental thing and a space also, or at least one of them, or they are not. If they are not, they have to explain where do these things come from. Now, for the bottom-up approaches, as I mentioned, they're kind of more fundamental, but much less developed than top-down approaches. So in bottom-up approaches, one of the things that they have to explain where does a space come from? What is a space? And it's not that hard compared to explaining that time comes from. So space can be, like, as I mentioned, a space can be, you can have a bunch of particles of a space, and then if you look at them from very far away, they make up this smoother space. But time is a very different beast, if you want. And even I don't know much, about the recent developments in string theory, but in loop quantum gravity, I know that there are very few works about really the nature. In loop quantum gravity, for the part I work on is called canonical approach, and it is basically you divide a space-time into a space and time. So you kind of foliate a space-time into a space sheets, and you move from one sheet to another sheet, and this is your time evolution. So what happens if you move on time
continuously or like in jump?
You have to do it continuously. That's the point. So what we do is that we quantize kind of each sheet of a space, but we really don't quantize time. So there are some works on that are like kind of about the nature of time and kind of time quantization, maybe a little bit, and where does time come from. But it's a few works and nobody's certain about them. So it's a very, I would say, a strong challenge for physics to explain time, because again, in canonical approach, as I mentioned, what happens is in gravity is gravity is really very different from other fields of the nature, because other fields of the nature, as probably your audience may know, there are four basic fields of the nature. One is a strong force, if you want, or a strong field, weak field, electromagnetism, and gravity. Now, the first three, the strong, weak, and electromagnetism, they describe basically matter content of the universe. However, gravity does not describe any matter content. Gravity describes the space-time on which the matter content is propagating or moving. That's why, first of all, that's the difference. And second, gravity, which is different in the sense that it describes or sets the causal structure of the universe. It tells you, if you don't have gravity, you don't know which particle came before what particle or after what particle, before, after, what caused what, is only defined by gravity. So if there's no gravitational field or a space-time, you don't know, there's no causation. Okay, so causal effect comes from gravity.
There is also one quotation of Einstein that event can never precede the cause. Causality.
Exactly. Yeah. Even the notion of causality is not possible without gravity. So, or the metric field, as we call that, the field of gravity, that sets all of these things. So when I don't know, maybe I missed what I wanted to mention, but when you want to talk about okay. So about the time, one thing that happens in gravity is that in canonical gravity, if you write the equations, you see that everything is frozen. So there is no time evolution. Everything is just fixed forever, and all the observables that we say are constants of motion, constant there.
So that kind of confirms that time is not a physical entity, but just a psychological.
We don't know that. That we see the time evolution anyway, so it's not just psychological. We see the objects moving.
Yes, most of the things and time are interrelated. Yes.
Yeah, so it's not just something that is in our heads. At least we think like that, and so that's the issue, right? The mystery, that it's called the problem of time in canonical quantum gravity. That the equations show you that there's no time evolution, but you have time evolution. So this is solved. It is kind of, there's several solutions for that. Most important of them probably would be, it's called the relational evolution. Relational evolution tells you that if you have only one particle in the universe, there's no space and there's no time. How do you know that this particle is moving? Because there's nothing around it to compare it, right?
Exactly.
So it is in relation with other things. So when you say that, for example, now it is 2 o'clock, now it is 3 o'clock. So you're comparing the position of the handle of the hand of the clock with the background of the clock, right? So how does one object change with respect to other object? That gives us the time evolution, although there is no inherent time evolution, something like that. But still, it's still mystery, and time is a very mysterious concept in physics.
And also, since you are a theoretical physicist, I want you to talk about the mind-body problem, measurement problem, that is generally not regarded by theoretical physicists as a serious problem. But I kind of think that it is ironic, because what we have done in physics so far is that we have regarded measurement to be an objective process. And we had to, because theory of consciousness was something that we knew nothing about. So what do you think about it? Like, what's your idea? What's your idea about the theory of consciousness? And do you think the consciousness process relates to the observation of particle that is generally adopted in quantum mechanical theories, like collapse of the wave function and things like that?
So let me just in 30 seconds explain what is the root of this problem, and then go to the answer your questions. Okay. So quantum mechanics comes with several conjectures or postulates, if you want. All of them are nice and good. So everything is evolving causally, if you want. Nothing is chance. But then physicists notice that if you use these postulates, what happens is that at the end you will have weird things like a cat that can be at the same time alive and dead. So it's not or, it's and. So alive and dead, a particle that can be here and there. And they actually experimented on that and said that, okay, that's true. Not on the cats, of course, but on one electron that can pass through two slit of like the double slit experiment.
I just want to interrupt here a little bit, because generally we say that in quantum mechanics, in quantum theories, a lot of weird things happen that are beyond human comprehension and human intuition, right? Then why is it that the example of the cat being simultaneously dead and alive so critical to this thing that you just explained?
That's exactly the point to your question. So so we know that in the world of particles, the small particles, you can have one electron that passes through two ways at the same time, right? But of course, the people that experimented on this said that, okay, let me see, if I have two slits and then I send one electron, it can pass through both of them. How about I just put something that understands if the electron is going through that or the other slit, and then see what happens. And then it turns out that the electron changes its behavior. It behaves like a particle and just goes through one slit. So it sounds to us that electron kind of knows, or at least the behavior of electron is based on how we observe it. If we observe it with a device that can detect that it goes through both slits, the electron will go through both slits. If we just kind of force it to go through one slit, measure it goes through one slit, it acts as a particle. The previous case was acting as a wave that can pass through both slits.
So electron is aware of its surrounding.
Yeah, so well, I'm not, that's what we don't know. So it may behave as a wave. So wave is not aware of its surroundings. So wave passes through both slits, right? If you have a water wave and goes through it. So the problem is not that the electron goes through both slits. The problem is that we assume that the electron is a particle, and it's not just we assume, because electron behaves as a particle in many cases, but also it behaves as a wave as many cases. So this duality was as mesmerizing physicists. So they put an additional postulate in postulates of quantum mechanics to be able to explain everything in nature. And that postulate says that at some point when a measurement is done, the wave function, as you mentioned, collapses. It basically means that the electron either behaves as wave or particle at some point. And then, actually,
if there is no disturbance, the electron behaves as a wave in that experiment. But if there is a disturbance in the direction, it becomes a particle.
Yes, exactly. So the electron goes, so either passes from one slit or the other if you do a measurement.
Yes.
So until here, before that, everything was good. Now you act, and this the fact that the electron goes from one slit or the other slit, if you do experiment, is absolutely random. So that is the problem. So there is one element in the theory. Until here, everything was causal. Evolution was causal, differential equation, everything. But at this moment of measurement, no one knows. It's just 1/2 possibility, like 50% possibility that goes here or the other one, and that's the element in the quantum mechanics that is random. Now, this raises two things. First of all, what is measurement important, or are we important? So is the measurement device, or are we? I mean, the humans measure things. I will get back to that. But the other thing that it raises is that so there is an element in the universe apparently that's not as just mentioning what Penrose says. So that's not computable. So what Penrose mentions, that the universe may not be computable, or consciousness may not be computable, is this, because this is absolutely random. There's no way to compute which of the slits the electron will pass through. So to go back to the first part, the consciousness and all those things. So yeah, people are thinking, okay, what is important, what is unique about measurement is that, well, in many of the opinions of many past physicists, is that we do the measurement, humans. So if we don't do the measurement, nothing else in the universe does the measurement. But then it is challenged by the fact that, well, we didn't do the measurement about many other things that happened before us in the universe. And so what happened there? And again, there are lots of discussion about that. So just to get an introduction. So
whenever whenever I talk or think about this problem, I get pretty nostalgic, because this was how I got started with the physics, because this was the first problem I came to think about organically through my thinking, because I was trying to calculate the speed of the neural waves in my brain to be accounted in the equation, and like to make some corrections in the equation. And then later on I realized that it is an objective process, so it is generally disregarded in the scientific community. And it was kind of like, I was pretty sad, because I was really optimistic about it. And then I came to know about consciousness and the work of Penrose. And so, like, since are you familiar with the work of Penrose regarding consciousness?
Yes, so to some extent, of course.
I think he has something like orchestrate objective reality, something like that, right?
Yes, it's called OR.
Yes,
and it's with Stuart Hameroff.
Yes, exactly.
The name correctly.
Yes, some biologist, right?
Biologist, yes. So he if I'm not wrong, he was working on microtubules.
Microtubules, yes, right.
Yeah. So he says that there are these things, these objects in all our bodies. There are some cells like that, and they come in various forms. Some of them are very symmetric. And they're found in our brain. And Hameroff apparently is the a doctor the medical doctor. He's work on. So when you want to for the before the operation, they want to give some drug to the person that doesn't feel anything, all those things. So he said that apparently those are the cells that are affected by these drugs. No one really knows about how does that happen, that your consciousness is turned off after they give you a drug for the operation. So really they don't know. They just use the drug apparently experimentally. I'm not sure about that, but I think that's the case. So the idea of Hameroff is that that's the case, that those cells are kind of the culprit of this process of the consciousness turning on and off. So Penrose was thinking about those cells, and how quantum gravitational effect can gravity basically can collapse the state of those cells, such that if most of those cells collapse to the right, if you want.
But gravity is too weak, right? How does it even?
So that's a quantum gravity effect, if you want. He was. I'm not sure about the details of the theory, or maybe it didn't work or something. So that was the basic idea, if I remember. So that's the collapse of wave function in one way, like conscious, or the other way, unconscious, using effects of gravity. But Penrose himself knows and mentions that these are These are very hard questions, because first of all, we are explaining consciousness, we don't know about anything about it. And then we are explaining it using quantum gravity, which we don't know anything about it.
Exactly.
And then that's...
But the thing that you said, the universe behaves independent of us, if that is correct, because if we humans are the only ones who are doing the measurement, then if that is correct, then maybe the problem of consciousness is not worth fighting for, worth working for. What do you think about that? Because the world is already consistent and the world looks pretty like complete with the theory of everything. We do not need a theory of consciousness as of now.
Well, I would say that that's not the case, because consciousness is part of the universe.
Mm-hmm.
So even if it's not affecting the measurement, that's part of the universe that we have to understand. How is that we have this consciousness and the stone doesn't have that, right? Even if we get the theory of everything, like now we have complete theory of like some scale, we have the quantum field theory completely, right?
Mm-hmm.
Or we have some other theories, but we cannot explain many of the complex behavior of the complex phenomena, right? Complex phenomena, you just apply the fundamental theory, but it doesn't mean that you know how it happens, because it's that's the name. Like we cannot describe accurately the pattern of the if tomorrow it rains or not, right? We cannot. If we didn't have any satellite, we couldn't really, because we can see that that's the snow is coming, all of that. So although we know perfectly the Newtonian mechanics and statistical mechanics, we cannot predict that, or we cannot say how really that happens to some extent. That's a very simple example, of course. But having the complete theory of everything, it just means that you know the fundamentals of how universe works. But applied to a very complex system like brain, that's another story, right? So I would say that doesn't finish with a fundamental theory of the universe. Now, consciousness, either it is, so there are two philosophies in that. That depends on your philosophy. If it's called dualist or non-dualist. So if you're a dualist, it means that you genuinely believe that, I call it philosophy because there is no, okay, let me talk about why I call it philosophy after this. But so if you're a dualist, it means that you genuinely believe that the universe is, the constitutes of the universe,
mind and body. Are you talking about Cartesian dualism?
Of physics and non-physical and non-physical objects, right?
Yes.
And if you're non-dualist, it means everything is physical, although they may look non-physical. So suppose that I give you my laptop and the screen, and it looks something subjective and like non-physical, but actually all the operating system, everything is the result of processes, electromagnetic processes inside the computer, right?
Yes.
So people use that as an example for how consciousness emerges. So you have some bunch of the neurons working together, a large number of neurons, and then that's the key. So it's a large number. And then that gives you something that is, so the sum of all is different from all, like something like that. All is more than, so you can see that in superconductivity too. So you have superconductivity that is the result of so many particles, not just, you don't have that in one particle, if you want. Consciousness can be this. Or dualist means that genuine universe is two parts. Non-physical or paraphysical, if you want, and physical. So based on your philosophy, let's say my philosophy at the moment is non-dualist. I think that everything is physical. In that sense, I can answer that question by this philosophy that so the consciousness probably comes from this process that emerges
out of the physical processes.
Out of the physical process, like wetness of the water emerges. That one molecule of water, doesn't make sense to be wet or not. I mean, it's a molecule.
Yes.
But the same thing happens with water. The same thing may happen with consciousness and many others.
Okay, and that's very interesting. And like generally, the theoretical physicists are like day and night working for big problems. Like they've come up with the standard model of cosmology, and from the biology side, we have the theory of evolution. These are the mainstream theories which dominate the scientific understanding of the universe, of the world that we live in. But generally, we can see that there is a kind of denial of science among the people, a disbelief in science, and this has only been triggered post 2016 Like we can see what sort of activities are taking place, especially in US, right? So people are skeptic about climate change and things like that. There is a disbelief in science that is increasing rapidly, like wildfire, all over the world. Like, how do you view this anomaly? Because physicists are and other experts, biologists, all of the scientists are working day and night. They are making an effort to understand the universe. But what we already have at our disposal is something that is not welcomed by the people. Whose welfare is the reason why the understanding of the universe got started in the first place. So it's pretty ironic. What do you think about it?
Even among scientists, if you present an idea that is at odds with what you believe or what you know, there's always an inertia, a pushback. So it doesn't matter. Even happens in science, but in science it's resolved easier, probably faster, because at the end you can logically describe. But at the end that happens anyway. I mean, if you go to people with calmness and logic and you say, explain, okay, this is that, and we know that, for example, if you say, okay, everyone should not use plastic from tomorrow, of course that will be pushback. Although that is the right thing to do, because that's not good for the nature, but there's ways to approach a problem and talk to the people. If you talk to the people from high, the high place, of course you get a pushback, and then it becomes a culture, and then people go, oh, these people think that they're better than us. And so these components, human components, are very important. So as scientists, we have to know how to reach to the people, be kind, be respectful, and of course, even if we know that they're wrong in many places, public relation is very, very important, as important as the substance of the argument itself. So that's my opinion. So,
but I think that disbelief in science is also because of the lack of understanding of what
that is another important factor that you mentioned. And that is, I mean, I mentioned these two factors because in these years, especially as you mentioned in the US, this is the thing that have become kind of the norm, that people shout at each other and nobody accepts what the other party or the other person wants to say. Unfortunately, this sort of kind of activism, both sides, that hurts people. Hurts both sides, because you cannot sit down and talk to each other. So yeah, but of course that's one factor. Of course, is unfortunately we scientists are not very good in public relations, in the sense, not in this sense, of course, that was another thing, but also in explaining things such that it gets attention of people. Like, for example, you see some of these documentaries, I really admire David Attenborough. He's really, I mean, one of my favorite scientists, and he brings the joy of science and the discovery and the mystery, everything to you, and how he narrates it and everything. He never does this talking to you from the high.
He doesn't push his agendas. He just lets people know what's the fact is.
Exactly, like we are, like all us are humans. We are discovering the world together. All those things. But there's not that many things like that in science, as you mentioned. So we have to. I am always for those things, that find good scientists that have good public relations.
So you think that it is the moral responsibility of scientists, even theoretical physicists, to come up to people and explain what their work is all about? Or should
I don't know about more, that's a strong, I mean, that's too hard to answer. Like moral, when you put moral the word there, so I don't know,
because in this pursuit of knowing, scientists have known quite a lot about the world, but what happens is a large fraction of the population is still unaware of even the basic understanding of science. So I really wish that scientists who are doing great things in their fields come up to people and explain what's going on, so that
I agree with that completely. I agree that this is very important. That is, I can say it's very important, very useful for the society as a whole. But I cannot argue from moral point of view. That's hard. I mean, that you have to think about it. Exactly. But there are parts. There are times that it is moral. I would say that it is immoral if they don't. For example, if you know that if you explain the COVID thing to people that you see, I mean, so if you know that if you explain that scientifically, lots of people can accept that and use this and mask and that. And if you don't do that, I would say that yeah, maybe that's not moral. So because you can evade an immediate danger to the society. But in general, I cannot talk about the morality that much.
Okay. And what do you think about people like Elon Musk? Like, at least given, like, let us not talk about his business, but he has definitely reinvigorated the passion of people about doing sciences, about going to Mars. And I also read his book, and he stressed that the future must be very inspiring, and the future where we go to Mars and have that interplanetary civilization is inspiring. That's why we need to get started with this process. So what's your overall idea about people like him who are at least driving the innovation in the right direction?
No, I don't know that much about this. I haven't thought about that, but I like that. I mean, we need some people that put their money in science and in innovation, and really they love it somehow. But we need these people that just focus on this part, like science and like going to Mars or making electric cars, or this is a few fields, and then do their jobs because they can do it much more better, because they have passion, they have more knowledge, they have money. So I'm all for those kind of people.
Okay, so now let us again come back to philosophy. Like, what difference do you think exists between philosophy and theoretical physics?
Oh, okay, that's a good question, because I wanted, when I was talking about the non-dualist and dualist, when I said it's a philosophy, I wanted to mention what I exactly mean. So at least from the history, what I understand is that people always want to know about things, right?
Exactly.
If you read the history a little bit, I know about it. Of course, I'm not an expert, but you see that everything, when we don't know anything about a phenomena, most of the time it starts with some kind of myth or religion about it. So so if you don't know about the thunderstorm, say that the gods are angry, or depends on your culture, where you are, right? Then it becomes, after some time, you become a little bit thinker and becomes philosophy. So philosophy is basically just the logic part of the science, if you want. It's not completely accurate, but logical part of science without experiment. So you think about it, okay, well, maybe that's, I always see, for example, so
a rational body of thought, at least.
Yeah, so you say that this should be that, because of this reason or that. Now, after that, you graduate into experimenting together with theories, I mean, with logical structure, and that's science. And at all of the time, if you look at the history, any unknown phenomenon starts in that way. So myth, and then philosophy, and then becomes science. And once it becomes science, it never goes back. That shows the science is the best thing we have. It's not perfect, but scientific method is the best thing that we have.
Yes.
Because if it was not the best thing, it would go to other realm of inquiry, like again back to religion. So this is what I meant by non-dualist and dualist philosophy, because at the moment we don't know, we don't have a science of consciousness, so we have to just take some just logical. We don't have an experimental evidence. We have to take some logical thing, and they're kind of, in many cases, they're absolutely valid at the same time, as you mentioned. So I mean, who knows, because we don't have an experiment. So yeah, so this is the difference between these three.
So what do you think is the limitation of science?
Well, in science, you always have to have some assumptions or conjectures or principles, and those, actually, you can see this in number theory, in Gödel's argument. So Gödel's incompleteness theorem, in simple words, says that if you have a theory with some assumptions, true assumptions, truth, based on which you can get new truth, right? So you say that
formal truth.
I mean, just a simple one, like you say that, okay, I have three principles. Okay, I take them to be true. I cannot prove them. I take them to be true, and then based on those three, I can derive like 200 new truths. But I know that where do they come from? They come from those three principles. However, there is at least one truth that I know that is truth, for example, somehow, but I can never derive from those three, and I have to add that to those three, so I get the fourth. Again, this goes on. So there's always
geometric proof, kind of, that the Greeks mastered in the ancient ages.
So yeah, so basically, it says that there's always truth outside of your formal logic, as you mentioned, outside of your arguments, that cannot be proved with your principles, but it is a truth. So that is shown in number theory. You can kind of say is that maybe that's most probably true in other fields of science. So also you have to, again, this is a different thing. So you always have to have some conjectures that you take to be true. Also, even if you take those things to be true, you cannot always derive all the truth of the universe from that. So you have to always kind of find new ones without this scientific method somehow. That's one of the weaknesses of science, of course. But no one can see at the moment how you can evade that. That's something that you have to start from somewhere.
The modern science has started just from 300 years ago. So there is a lot to go, given that we are trying to understand the universe that is 14 billion years old. And the history of science that we have been doing, it's only, let's say, at the most, it can be 2000 years, but not more than that. So we can be optimistic of a better scientific understanding in the coming centuries, right?
Of course. No, I mean, you can actually, I don't know if it's possible, but we can actually hope for a new method. Better than scientific method.
Yes.
But at the moment, that's the best we have, and it really does good. I mean, look at us in 100 years, if you say 300 years at most.
Yes.
We have discovered what has happened until the very
beginning of the universe.
Beginning of the universe, and yeah, that's amazing.
Amazing, yes. As well as the technology. Look at the technology, not just the theoretical understanding of the world we live in, but also we have supplemented our day-to-day life, made it much easier than it used to be. Now let us come back to the topic of relation between theoretical physics or physics and mathematics. Which one do you think is more important? Just give me one word answer.
So you know that they are different nature. Mathematics is not science.
Exactly.
Science is accompanied by experiment. Mathematics is not. So,
yes.
But I would say that probably mathematics.
Probably mathematics.
One word.
Okay, so if I have to explain the scenario, like when you are just starting to understand the world, you do it through the process of science, and in order to make science valid, it has to be based on some mathematical structure or logical structure that you said. So it needs to have some mathematical formalism. So in the Newtonian physics or classical physics, mathematics is extremely important. But when you go to higher quantum field theories, then we have the paradoxes of theoretical physicists like Edward Witten getting Fields Medal. And so what is going on here? Like, how does a theoretical physicist end up getting a Fields Medal in mathematics? Like, can you please explain?
I think Ed Witten was a mathematician, if I remember correctly.
Yeah, he started as an economist and a mathematician, yes.
Right.
But he was you understand my question, right? He was a quantum field theorist, but he ended up getting Fields Medal.
Because his work, he contributed a lot to the mathematics. String theory in general has contributed, like other quantum gravity theories, but I would say string theory even more. So now you see that I'm not religious about loop quantum gravity. I'm just I like all the inquiries about quantum gravity. So string theory is one of the theories that helped a lot to the theory of mathematics. So that's kind of natural. Like if you kind of but at least open a new front in mathematics, that's they should give you they may give you a Fields Medal.
Do we have sorry to interrupt, do we have the mathematics of quantum field theory right now?
Yeah, quantum field theory is something that is kind of pretty well established, and mathematics of quantum theory is basically, I would say that, it's basically differential geometry and calculus and that thing. So differential geometry is kind of well known to a lot of degree. Of course, there are things. Of course, physicists helps a lot in that. For example, in something called symplectic geometry, that is corresponds to the classical mechanics and quantum mechanics, mostly classical mechanics, if you want. That was kind of physicists opened that front for mathematicians. But so the mathematics is kind of known. The problem is that we don't know how to solve the problems in mathematics. Like, we know perfectly well about differential equations or even algebraic equations, but there are algebraic equations we cannot solve. That's the problem in most of the science in the mathematics. It's not that we don't know mathematics.
We cannot solve them algebraically, but we can solve it using other computational methods, right?
Yes, we can solve them numerically. So yeah.
Yes.
But we are not always happy with those. So we need some analytical approaches too. Like the Fermat's last theorem. It was when it was proven, then everybody was happy, and they gave the guy the prize. But of course, you could with computer, you can always go with higher and higher degrees of the exponent in the equation and say that okay, this is true, but it's never a proof because there may be the next one that is not working.
Okay. So so this is like the unreasonable effectiveness of mathematics. There is a very famous phrase in physics, right?
Yeah.
It was coined by Eugene Wigner, I guess. So like you stress the importance of communication of scientific theories to the people. In this regard, like what do you think is more important for the world? Does the world really need to focus on improving the lives of the people through technology, or should it focus more on the abstract understanding of the physical world that might not be handy anytime soon? Because
I think they're not
even when we have
exclusive.
the theoretical understanding of the evolution of the universe, that is not going to be beneficial to a man on the street. So we as a species, should we invest more on the technology and should try to improve the living standard or well-being of the human species, or should we try more to understand the universe we live in? Which one is more important?
I'm not sure about the statement that knowledge of the beginning of the universe is not useful to the ordinary person. I mean, us also.
No, I mean like directly, anytime soon.
Even directly, look at there was this quote, I don't remember where I read it, but it says that there is no field of science that has once been abstract and in future has not evolved into something that the human life has benefited from that. I mean, look at the quantum theory that people were just discussing academically if the electron goes from this or that. I mean, but later that turned out to be all of these imaging devices and in the medical practice, and later, the quantum computers and all those things that will really increase the quality of life. So who knows? Until now, every scientific discovery that has been this abstract has helped human life. Who knows? Maybe if we know about the center of the black holes at some time, it may help us. We don't know that, right? So, so that's the statement. I'm not sure about. But I would say that these are not mutual. Even if it was the case, they're not mutually exclusive. So you can at the same time put some part of your money and resources on technology and some part of your money resources on basic sciences.
Okay, so like as someone, Iran is also considered to be a developing country, or like what is the
Iran
status?
is a developing country.
Developing country. Okay, as someone who started from a developing country and you ended up being a professor of theoretical physics in Canada. So like having lived through this life, like what message do you want to give to young students in developing countries about pursuing their studies in fundamental science?
Well, so the general, I mean, it's a cliche, but the general message is that just you have to work hard, you have to go for your passion. That's very important. And also, the world is unfair. Don't blame others for that. That's how the world is. And just try to take your responsibility, do your hard job, and remember that most of the cases, it's that your life is in your own hand. So, I mean, not always. Most of the life, many of the parts of the life are accident. And from the time you're born and where you're born and how you see someone in somewhere that may help you go to this university or get married or whatever, but still we have important part in our lives, and yeah, you have to take advantage of the opportunities that we have.
So I must tell you that it's an honor to have you here with me, and I'm hoping that I can I get to talk to you like this again and again, and I'm really looking forward to other amazing discussions with you. Maybe sometime I hope I can you will be available in the next time as well.
Of course, in the next time, but we can arrange that for that. I really enjoyed it, and thank you very much for having me. So I really like that. I mean, as you know, I mentioned that I like public thing about science and practical. And also, I mean, we had a very nice summer in ICTP together. So when you asked me, I was really glad to do that.